Hi, my name is Shavina Ravichandran.
My name is Daihat Menking.
Hi, so my name is Muhammad Ihsan Bibda Iskandar.
Hi, my name is Nur Alisha Adriana.
Hi, my name is Anna Maria de Sanz Pinheiro.
And now I'll be presenting the introduction for our project, which is production of ammonia. Ammonia is one of the most important chemicals in the world, and it is a colorless gas with strong and pungent smell and is widely used in many industries. Its main application is in production of nitrogen-based fertilizers such as urea and ammonium nitrate. Besides that, ammonia is also used in manufacture of nitric acid, explosive, refrigerative system, and also industrial cleaning products. Commercially, ammonia is produced using the Haber-Bosch process, where nitrogen gas reacts with hydrogen gas over an catalyst at high temperature of around 400 to 550 degrees Celsius and high pressure of 150 to 200 atmosphere. This reaction is exothermic, meaning it releases heat while producing the ammonia. To analyze and design this process, chemical engineers apply mass and energy balance. So the mass balance ensures that the amount of material entering the system is equal to the amount of material leaving the system, taking into account any generation of consumption due to chemical reactions. Okay, so the energy balance applies the first law of thermodynamics to determine how heat transfer throughout the process. So these calculations are essential for designing a safe and efficient industrial plant. So before performing the calculation, we also perform degree of freedom analysis. So a degree of freedom analysis means the system has enough independent equations to solve all the unknown variables, indicating that the process is mathematically solvable. Besides process calculation, fluid mechanics also plays a very important role in ammonia production. Since gas and liquid ammonia is transported through a pipeline, engineers need to analyze the flow behavior inside those pipes. This is done by using Reynolds number, which determines whether the flow is laminar, transitional, or turbulent flow. The friction factor, the pressure loss are then calculated to minimize the energy consumption and ensure efficient transport of material throughout the plant. And finally, the extended Bernoulli equation is used to evaluate the overall mechanical energy changes within the piping system. So in summary, this introduction provides the theoretical foundation of our project by combining the principle of chemical engineering and also the fluid mechanics, which are essential for designing an efficient and reliable ammonia process.
I will be presenting on the principle of chemical engineering part, and I will start with the flow diagram first. Firstly, we have a mixer and compressor. Fresh nitrogen and hydrogen combined with recycled gas in a mixer, then compressed to 200 atm at stream S1. On the next, we have heater. Stream S1 is heated to 400 degrees Celsius to activate the catalyst and exiting at stream S2. The conversion reactor in the reactor unit S2 undergo exothermic synthesis over ion catalyst at 25% single pass conversion and leaving as S3 at 450 degrees Celsius. And then we have the cooler. This is a non-reactive unit that cool down the stream to 35 degrees Celsius and prepare ammonia for condensation. And lastly, we have the separator and pump P1. Liquid ammonia separate at the bottom and is pumped out by the P1 as our product. The unreacted nitrogen and hydrogen gas return via the recycle line back to the mixer and completing the loop. For the mass balance part, the cooler is the non-reactive unit and as the conversion reactor as the reactive unit. The Haber-Bosch process for ammonia production begins with a fresh feed of 75% more hydrogen and 25% more of nitrogen, which is a mixed recycle stream, heated to 400 degrees Celsius, and fed into a conversion reactor operating at 200 atm, where the reaction N2 plus 3H2 equals to 2NH3 occurs over an ion catalyst. Mass balance is the foundation of chemical engineering because it tells us how much material flow through the system, where each component goes and whether conservation of mass is satisfied. Without this, we cannot size equipment or design recycle loops. For the cooler as the non-reactive, the mass balance confirms that the composition does not change. All 225 kmol per hour of hydrogen and 75 kmol nitrogen and 50.545 kmol per hour of ammonia entering simply live at the same flow rate at lower temperature, providing that mass is conserved and no reaction occurs. For the conversion reactor as the reactive unit, the mass balance shows that 25% past conversion of nitrogen, 25 kmol of N2, and 75 kmol of H2 consume of produce 50 kmol per hour of NH3, leaving 75 kmol N2 and 225 kmol of H2 to be recycled back to the mixer. This confirms that the stoichiometry of the reaction is satisfied.
Next, I will continue with energy balance analysis for our ammonia production. Specifically, I will explain about the energy balance for non-reactive unit, which is cooler, and the reactive unit, which is conversion reactor. First, I will explain about the energy balance for cooler. The primary function of the cooler simply just to remove the heat from the process before it enters to the separator. Since no chemical reaction occurs, only sensible heat change are considered. Before performing the calculation, there are several assumptions that we make. First, the process operates under steady state condition, meaning there's no accumulation of mass or energy within the cooler. Second, no chemical reaction occur inside the cooler. Third, no phase change take place, so all the components remain in gas state. Next, changes in kinetic and potential energy are negligible. We also assume that the shaft work is zero, meaning the cooler performs no mechanical work. Furthermore, the pressure drop across the cooler is negligible. And lastly, the heat capacities across the component remain constant. With all these assumptions, the general steady state equation become more simpler. So the equation is Q equals to H out minus H in. The inlet stream enters the cooler at 450 degrees Celsius, while the outlet stream leaves the system at 35 degrees Celsius. The total inlet enthalpy is 5170.91 kilojoules per hour, and the total outlet enthalpy is 98.69 kilojoules per hour. Q equals to negative 5072.22 kilojoules per hour. Let's continue with conversion reactor. The reaction inside the reactor is nitrogen will react with 3 hydrogen will produce 2 ammonia molecules. This reaction is exothermic, meaning that it will release a lot of heat. For this energy balance, the following assumptions are made. First, the reactor operates under steady state condition. Next, the reference state is 25 degrees Celsius at 1 atm. No shaft work is performed. Change in kinetic and potential energy are negligible. The pressure remains constant at 200 atmospheric pressure. Since the chemical reaction happens inside the system, the energy balance must include the reaction enthalpy. So the equation will be Q equals the extent of reaction multiplied by the standard heat of reaction plus the outlet enthalpy minus the inlet enthalpy. This equation accounts for sensible heat of the process stream and the heat released by the chemical reaction itself. The extent of reaction is 25 kilomoles per hour. The standard heat of reaction at the reference temperature is 92,400 kilojoules per kilomole. Multiplying these two values will give the total reaction heat, which is negative 2,310,000 kilojoules per hour. So the total inlet enthalpy will be 4,919.60 kilojoules per hour. For the outlet stream, the calculated sensible enthalpy is 5,170.91 kilojoules per hour. The Q equals to 2,309,748.69 kilojoules per hour. Next, I will pass to my friend to continue the presentation.
Okay, so I will present section 3.1 and also 3.2, which is covering our methodology for pipe sizing and also the pressure drop calculation from pipeline 1 until 5. So in section 3.1, basically our primary goal is to select a proper pipe diameter that keeps fluid velocity within economic limits. So basically, as we know, if velocity is too high, it causes an excessive pressure drop and also can cause erosion of pipe. So if it's too low, pipe costs become unnecessarily high. So by that, we follow 3 four-step calculation framework, which is as we know, fluid velocity, which is V equals to QA, and Reynolds number, which is RE equals to rho VD over viscosity, to check the flow regime. And also we need to calculate the frictional loss, which is from fanning friction factor equation. And also we can calculate also the wall friction as well, and also its minor losses, which is K fitting, and also we can calculate pressure drop from it. So moving on to the pipeline number 1. So pipeline number 1, basically it using a 4-inch pipe, which is the velocity is around 20.67, producing a pressure drop which is 543.02 Pascal. And moving on to part 3, part 2, which is fresh hydrogen feed. Also in a 4-inch pipe, because hydrogen has a very low density, which is 0.0824 based on my calculation, and also the velocity reached 62.01 with a pressure drop 362.68 Pascal. So let's going to the flow, which is P3, which is mixer to the preheater, and also P4, which is preheater to the heater, and lastly, which is P5, heater to reactor. So what can I summary for my pipe, which is using a 4-inch pipe for fresh feeds and 6-inch pipes for the main combined stream gives our fluid velocity in optimal range and minimize water pressure. So that's all. So my friend will explain more on P6 and until P9.
Alright, moving on to chapter 3, I will walk you through our fluid mechanics calculations starting from pipeline P6 through to our planned conclusion. For pipeline P6, which connects the conversion factor to the cooler, we evaluated a gas mixture stream at 120 kilograms per cubic meter density, operating under turbulent flow with a Reynolds number of 4.6 times 10 to the power of 5. The resulting pressure drop is 22.32 pascals. Next, pipeline P7 carries the cooled gas mixture from the cooler to the separator. With a higher gas density of 150 kilograms per cubic meter, the pressure drop across this 2-meter segment is 16.05 pascals. Moving to pipeline PA, this line transports liquid ammonia from the separator to the storage tank. Because liquid ammonia is denser at 682 kilograms per cubic meter and flows at a lower velocity, the pressure drop here is very low at 1.47 pascals. Finally, pipeline P9 handles the unreacted recycled gas returning to the mixer. Across its 8-meter length and multiple fittings, the pressure drop comes to 406.5 pascals, which is our highest pipe loss due to line length and fitting resistances. Beyond pipeline calculations, we designed our product delivery strategy. We selected a sealess centrifugal pump operating at 85% efficiency to prevent hazardous ammonia leaks. To accommodate 2 days of production at an 85% liquid filling limit for thermal expansion, we sized a horizontal carbon steel pressure vessel with a total capacity of 71 cubic meters. In conclusion, our plant design successfully integrates mass and energy balances with practical fluid mechanics. All calculated pipeline pressure drops remain within highly realistic ranges for preliminary design, proving the operational feasibility and safety to our proposed system. Thank you.